get that done. Like I said, I gave everybody 2 weeks to do it just in case, but there, then I'm not bouncing like that. Okay. But any questions that you wanted to go over before you started the test, or anything that you're trying it that's confusing or you haven't quite got there yet?
Yeah, I'm doing okay so far.
All right. It's good so far. Awesome. All right, so we are going to start chapter 5. The goal is to finish chapter 5 before break. So, which is obtainable. It's only 5 sections. One of those being like, I think the first one has a lot, but the second section is 1 through 9 odd. So that barely even counts as a section, right? It's like a subsection. And then, yeah, so there's only basically 4 sections that we have to go over in the next 2.5 weeks. And hopefully we'll just kind of wrap up early and we'll be good, right? That's the goal for you guys. So what we are going to talk about today is called using fundamental identities. And so let's talk about what the fundamental identities are. These are all actually, well, most of them should look actually pretty familiar based off of all the other trig work that we've done. I'm gonna kind of scoot this over so I can see the chat, Sarah. If you chat, I don't want to exclude you. So I'll put the chat there, and I'll put my fundamental trig identities here, and then we can see both. Okay, so the first 6 should be, actually the first 8 should be very, very familiar to you back from chapter 4. So these are what I kept calling inverse, but the reciprocal identities. The first 6 is what we talked about. Well, you're welcome, Sarah. I want to hear what you have to say. All right, so these are our reciprocal identities, right? Oh, what's my computer doing? And we've talked about these lots and lots and lots of times, right? So basically, if you have the sine of a theta or a u, that's equal to 1 over the cosecant of u, right? And so that's just what it is, right? So if the sine of u was pi over 3, then the cosecant of u would be 3 over pi. Okay, they're reciprocal to each other. So it's sine and cosecant, cosine and secant, and tangent and cotangent. Right? And then that also works if you have the reverse. So if you have the cosecant, that's equal to 1 over the sine. So that's just basically rewriting it the opposite way, right? And then you have the secant is 1 over the cosine, and the cotangent is 1 over the tangent. All right, so those are all review from chapter 5, or 4. We're in chapter 5. Those are all review from chapter 4. Then the next one is, again, review. So we have that the tangent of u equals the sine of u over the cosine of u. Okay, this one we can kind of derive pretty easily, right? Because if you think about your SOHCAHTOA, right? The sine is the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse. And when we have a weird fraction like that, we get to cross out since they're the same denominators, and we end up with the opposite over the adjacent. And by definition, SOHCAHTOA, the tangent is the opposite over the adjacent. So you can do a really quick derivation to kind of see that that's true, right? And then the cotangent of u, which is 1 over the tangent. So 1 over the tangent is the cotangent. Just means that we're going to flip the sine and the cosine from the top to the bottom. Okay. So those are all kind of review-ish. The next set is a set of Pythagorean identities. It really wants to do that whenever I make this motion on my screen. I'm just trying to draw a line and I think it thinks I'm swiping. Okay, so the next thing that we have is the Pythagorean identities. So this says if we have sine squared of u plus cosine squared of u, that equals 1. All right, so that's one of the Pythagorean identities. We also have 1 plus the tangent square of u equals the secant squared of u. And we have 1 plus the cotangent squared of u equals the cosecant of u. All right, so the first thing I just want to point out is why they write this little square the way they do. It's because you don't want it to think. So if I had the sine squared of, I don't even know, let's see, pi over 3. Right? We don't write the squared out here because the squared, it's not pi over 3 squared. It's not that, right? It's really sine of pi over 3 squared is what it means. But you get to write it kind of in this fun little way right next to the sign. So that's kind of what it means. And these are just 3 identities I can show you on, you can put them in Desmos because we're going to use this for the cofunction anyway. You can put these in Desmos just to kind of play with them and you'll see that they are true. So what I mean for, well, I won't do all these, but if you do the sine squared of x plus the cosine squared, nope, not the con. I don't know what that would be. Cosine squared of x. And if it graphs it, you could see it knows that it's always 1. Okay, so you're basically adding these 2 curves together. I know, I'll take that away. You're adding the sine and cosine curve together. It's kind of cool, right? This sine squared and cosine together. And you can see, like here, if you add them together, it's 0 plus 1, so it's 1, right? Here it's 0.5 plus 0.5. Here it's 0 plus 1, so it always basically adds up together to give you 1, and you add them together. Okay, if you do, just so you can see, our second Pythagorean identity, if we do 1 plus the tangent squared of x, we can remember we have a weird tangent always has some asymptotes due to the fact that you're dividing, it's a ratio. And then if you do the secant squared of x, you'll see that they overlay. So it's just kind of one of those things. We're not going to derive them all unless you really feel like it. All right, and then the same thing with the cotangent and the cosecant. Okay, and then the last little section here, this cofunction and the odd-even identities, we'll do some problems with those. The ones at the top are probably the ones that you're going to use more. But I think it's important to note this idea of cofunction identities. So this you might have noticed back when we were talking about graphing sine and cosine curves. So if you graph the sine of x, right, and the cosine of x, right, they're the same, periodic function, right, but they're shifted by a little bit. So one of the identities that mathematicians have come up with is that if I shift my sine graph by doing pi, where are you at, pi? There we are. If I shift my sine graph by doing pi divided by 2 minus x, okay, then it overlays with the cosine curve. So really, it's still a sine curve, you're just shifting it, right? and then you produce the cosine curve. Likewise, if you have a cosine curve and instead you can shift it to make it the sine curve by subtracting the number from pi over 2. Okay, so those are some ways to kind of, it's basically showing you this two graphs are the same, they're just being shifted by pi over 2. All right. The same with the tangent and cotangent. Those are the same graphs. They have a difference of where their starting point is of pi over 2, so we can shift them. And then the same relationship exists between the secant and the cosecant. Those are shifted by pi over 2. Okay. And then our last thing is kind of an interesting little one, is the even and odd identities. So what this is that it's talking about if you have a negative that you're taking a trig function, you're taking the sine of a negative pi over 2. Okay, so what this is saying is that if you take the sine of negative pi, oops, not equal. Uh-oh, I think somebody's microphone's, is that my microphone? Oh, that stopped. Hopefully it's okay. All right, so if you take the sine of negative pi over 3, okay, that is the same as taking sine of pi over 3 and making it negative. They're the same. So if you have a problem where it says take the sine of negative pi over 4, you can just find the sine of pi over 4 and then just make it negative. You're allowed to do that. Okay, so that's kind of a nice feature, right? Nice feature of trig functions. I didn't mean to make that big. Sorry, I'm still trying to see the chat and that. Okay, so you can do that for the sine, right? The sine, if you have a negative inside, you can just put it on the outside and take the regular. You can do that for the tangent. If you have a negative on the inside, you put it to the outside. You can do that for the cosecant. Okay, if you have a negative on the inside, you just pull it out. And you can do that for the cotangent. Okay, but of course, we couldn't just have the rule for all. We have to have cosine and secant had to be a little bit different, right? So sine, tangent, cosecant, and cotangent all have this ability. If you have a negative, like you're taking a negative that's inside of your trig function, you can just pull the negative out at the end, right? Cosine and secant don't have this ability. They actually have a different ability. It's like their superpower, right? If you take the cosine of negative pi over 3, that's the same as just basically you get to just ignore the negative. So whenever you have a negative inside a cosine, you can just basically ignore that it's even there and just take the cosine of the positive number. And the same with the secant. If you have a negative number inside the secant that you're taking, you can just ignore it. So I don't know. Maybe the cosine and secant have a better superpower than the sine, tangent, cosecant, and cotangent. Possibly. Maybe. All right, so now that we've learned all those exciting properties, I bet you guys cannot wait to use them. Right? Like, oh, wait, I just learned all these. I can't wait to use them. So that's what we're going to do. Okay. So, when you're doing your homework, keep these in mind. Okay. And we're just going to kind of go through a bunch of these and see see where we get, right? Just looking how I organize this, yeah. It's kind of weird on your paper. So if you're looking, you're like, Okay, so let's go ahead and do some examples. All right, so it says in exercise 1 through 14, use the given values to evaluate, if possible, all 6 trig functions. All right, let me get out my notes. I didn't even have my notes out. There we go. So this is kind of just like our, just like we've been doing the whole time. It's just reviewing what these 6 trig functions are and the relationships to each other. So I think we should do number 6 because it's a fun symbol to write. I forget what that Greek letter is. I don't know that one off the top of my head, but it's fun to write and it's different than writing x or theta. So let's do number 6. All right, so number 6 tells us that the cotangent of this fun Greek letter is -5. Oh, is it pi? Phi? Phi? Pi? Pi is it pi? Phi. Sarah, which way am I saying it? Phi? Not pi. Okay, phi. Got it. Phi. I just wanted to write phi because it looked fun. Okay, so this is the original problem. We have the cotangent of phi equals -5, and the sine of phi equals the square root of 26 over 6. So then so we have 2 out of 6 functions, right? The easiest ones to do are going to be the reciprocal functions, right? So the reciprocal of the cotangent is the tangent. And the tangent of phi is just going to be 1 over 5, and it's still negative. So now we've got halfway done, right? Also, we're going to do the reciprocal function of sine, which is cosecant of phi, right? Again, all we have to do is we have to flip the numbers. Okay, so this is correct, but then math-wise, we don't like it so much, right? Because we need to get rid of the square root in the denominator. So you're actually going to end up with 26 times the square root of 26 divided by 26, which we just end up with the square root of 26 is the cosecant of phi. Okay, so we did all the easy ones. Now we have to deal with we got to find the cosine, right? And we have to find the secant. Okay, so if you remember, I think the easiest way for me to do this is I know the tangent and I know the sine, so I know that the tangent of phi equals the sine of phi over the cosine of phi, right? Or another way I could write this is if I did my cross multiplying, I could say the cosine of phi equals the sine of phi over the tangent of phi. Right? I just swapped these when I basically did that. So now we know that what the sine of phi is. It's square root of 26 over 6. And the tangent is -1/5. Right? So the cosine would be -5 square root of 26 divided by 6. If you can even read my writing. -5 square root of 26 divided by, did I write that right? 26, sorry. 26 by 26. And then to find the secant, right? The secant, you're just going to flip that and solve it. So the secant, if you're doing it, ends up being negative square root of 26 over 5. Okay, so kind of review-ish, right? If you look at something, I'm not going to do the whole thing. If you look at something like number 8, okay, it says the cosine of pi over 2 minus x equals 3/5. So if you see that, you might have some, like, maybe not yet, but might have a little bit of alarm bells in your head going off, and you're like, well, what does this mean, right? If you go back to your chart here, right, you'll see that the cosine of pi over 2 minus x is the same as the sine of x. So instead of having this weird cosine of pi over 2 minus x, you could rewrite this as sine of x equals 3/5. And then you have the cosine of x equals 4/5. And then that's a really easy problem to go from there. Okay, looking down the road here, you have the cosecant of negative x equals negative 5. So then again, look back at your chart and say, oh, well, if it's negative, if the cosecant is negative on the inside, I can rewrite this as negative cosecant of u or x or whatever it might be. So another way I could rewrite this is negative cosecant of x equals negative 5, or the cosecant of x equals positive 5. So some of them might kind of give you a little trick as to what that means. And then the last one I want to point out here is number 14. It says the tangent of theta is undefined. Okay, the tangent of theta is undefined. What does it mean when well, the tangent, remember, is the sine over the cosine. So in order for the tangent of theta to be undefined, that means that the cosine of theta has to be equal to what? It means that the cosine has to be equal to 0 in order for the tangent to be undefined. So it's kind of like a little puzzle, right? You got to kind of think through, what does that mean? What does that mean, right? All right, so let's keep going on some examples, just kind of get through all this good, fun stuff, right? Okay, so, oops, forgot to erase you up here. There we go. Okay, so number 15 through 20, it says match the following trig expressions with one of the following. Okay, so you have to do 15, 17, and 19, but let's look at maybe, let's look at 18. Okay, so number 18 is 1 minus the cosine squared of x times the cosecant of x. So when you see this 1 minus the cosine of x, whenever you have that, cosine squared of x, whenever you see like that squared value in there, you want to be thinking, can I use one of my properties, my Pythagorean functions? So I know that the sine squared of x plus the cosine squared of x equals 1. Okay, so that means if I subtract the cosine squared of x from both sides, I get that the sine squared of x equals 1 minus the cosine squared of x. So what's another way that I could write this? I could write 1 minus the cosine squared of x as the sine squared of x, okay, times the cosecant of x. All right, well, let's think about this. What is another way you could write the cosecant of x? So you have the sine squared of x times the cosecant of x, which is 1 over the sine of x. So because we have a sine squared in the numerator and a sine in the bottom, we can basically cross one out and we're left over with the sine of x. So this number 18 could actually be written just as the sine of x if you reduce it down. Okay, so that's kind of how that works. Does anyone want to see another example of that? Because we're going to be doing a lot more of that. Well, actually, let's just do number 20 really fast because that one's easy. So if you see number 20 there, right, we have the sine of pi minus 2 minus x over the cosine of pi minus 2 over x. So what is another way to write the sine of pi divided by 2 minus x? Again, look back at your sheet, right? Let me make this sheet smaller here. Not bigger, smaller. Smaller. And it's okay to refer back to this, okay? Ugh. Having problems with Windows and popping out today. No, I'm trying to make you little so I can see it. All right, really just wants to stay here. Well, all right, so I know that the sine of pi minus 2 minus u equals the cosine, and the cosine of pi divided by 2 minus u equals the sine, right? They just basically have this kind of funny relationship. So I could rewrite 20 as, instead of sine of pi minus 2 minus x, I could write that as the cosine of x. And the cosine of pi minus 2 over x is the sine of x. And another way to say cosine of x divided by sine of x is the cotangent of x. So number 20 would be C. Okay. And that's basically what you're going to do for these and these. You're going to be rewriting the trig expressions by kind of playing with their different properties. So why don't you guys try number 26 and tell me what letter you think that matches up to. So try number 26, which is the cosine squared of pi divided by 2 minus x over the cosine of x. There we go. So try number 26 and I'll start writing it on here. Okay, so if you see on the screen here, nobody told me what their letter was, so you guys were afraid to say it first, right? Did anybody get D for number 26? You're not telling me. I can't hear. All right, I'm going to assume you guys all got D. All right. So what you do is you have the cosine squared of pi divided by 2 minus x. So that's your signal that, okay, I'm going to switch that. So I can rewrite that as the sine squared of x. Okay, you're allowed to do that. I know you might be a little confused because it had a squared and it had the pi minus 2, but you can rewrite that as the sine squared of x over the cosine of x, right? If I take one of those signs out, I kind of skipped a step. So if I rewrite this as the sine of x times the sine of x divided by the cosine of x, right? One of these, sine of x over cosine of x, becomes the tangent of x times the sine of x. Okay? So that's, I mean, we're just basically going to keep chugging through this. The whole thing is kind of like this. They just get a little more complicated for each one. Okay, so in the next little section in 27 through 38, it says use the fundamental identities to simplify your expression. And you guys can send me a message if you're not getting it, because I want to make sure everybody's getting it. But I'm going to just keep going unless I hear otherwise, all right? All right, so use the fundamental identities to simplify your expression. Use the table feature to check your result numerically. You could also use you could just look at a table or a graph. Either one would be okay. Okay, so what I mean by this is if you're doing these problems, you want to be able to check and make sure that you're doing them correctly, like you're basically you're simplifying trig functions, right? So for example, number 28 is the cosine of beta times the tangent of beta, right? So I know that another way to write the tangent of a number is the sine of beta over the cosine of beta times the cosine of beta, right? So if I have this, then I know I can cross my cosines out and I'm left with this is the sine of beta. So another way to say cosine of beta times tangent of beta is the sine of beta. They're equal to each other. And then what it's saying is that you can go into your graphing tool and you can check this by just putting these two trig functions in. So in Desmos, we have the cosine of x, can't put beta in, right? Cosine of x times the tangent of x should equal the sine of x, because that's what we just calculated, right? And they do, the two overlay on top of each other. You could turn it into a table, or you can just look graphically that, yes, those match up, right? The points are the same. So you can actually check all of your crazy trig work to make sure that you're on the right track. Okay, a little bit more complicated, like number 34. It's the tangent squared of theta over the secant of theta. Okay, so whenever you see tangent, a good thought is to maybe convert that into sine and cosine. So we could think of this as the sine squared of theta over the cosine squared of theta. Okay, and then we have secant on the bottom. So another way of thinking of secant on the bottom is to think of that as cosine squared on the top, right? They're reciprocals of each other. So if we rewrite tangent as the sine squared of the cosine squared, and we rewrite the secant as 1 over the cosine, then all of the sudden I have a cosine squared in my numerator and denominator that I can cross out, and I end up with the sine squared of theta. Okay. So you can check all these by throwing them in a graph really quickly. Shall we keep going? Very exciting, right? Oops. Okay, so let's see how many more examples. I just want to see as many examples as we can get done in this last. We have like 10 minutes or less, right? About 10 minutes. So let's see, let's just keep kind of plowing through examples, because I think the more you see, the more it's like, okay, I can do this. I got it. So let's look at number 40. 40 is like a different take on what we just did. So the blah, blah, blah. Number 27 through 38, you're just simplifying. And 39 through 44, they actually give you what it equals to, and they want you to try to figure out the steps to get there. So they tell you the answer in 39 through 44, but you just don't, you have to figure out how to get from one to the other, or to right here, okay? So what I mean by that is if I'm doing number 40, okay, it says that I have the secant of theta minus the tangent of theta times the cosecant of theta plus 1. Okay, and I know that this should equal the cotangent of theta. So what I need to do is I need to take this and simplify it down to get the cotangent of theta. So what I like to do when I do these problems is I like to put everything into sine, cosine, and tangent. Or actually, I like to try to get everything down to just sine and cosine and see what I can get out. Okay, so what I mean by that is instead of writing the secant of theta, I'm going to write this as 1 over the cosine of theta. Okay, minus, and then I have the tangent of theta, so I'm going to write that as the sine of theta over the cosine of theta. So if you can get everything down just sine and cosine, then a lot of times you can do something with it. Okay, and then I have the cosecant of theta, which is equal to 1 over the sine of theta plus 1. Okay, so then what do I notice here? Well, I notice that I have the same denominator, so I can rewrite this as 1 minus the sine of theta over the cosine of theta. Okay, so that's kind of cool. I can do that, right? Let's see, what else can I do? I'm thinking what I want to do next. Okay, I know what I want to do next. I want to be able to just simplify this together. So the second part, I'm going to rewrite this as 1 over the sine of theta. But if I want to add 1 to it, I'm going to rewrite 1 as the sine of theta over the sine of theta. So that way I have like denominators again. So now I have 1 minus the sine of theta over the cosine of theta times 1 plus the sine of theta over the sine of theta. right? Okay, so now I want to combine my sines and my cosines together. I want to do, well, I'm multiplying, right? So now I can actually multiply. Sorry. So I can multiply my top, which is 1 minus the sine of theta times 1 plus the sine of theta. And then my bottom becomes the sine of theta times the cosine of theta. Have I lost you guys yet? This is the most complicated part. Not yet. You're still there? All right. All right. So now how do you think we simplify this? We have 1 minus the sine of theta times 1 plus the sine of theta in parentheses. Does this look like a FOIL kind of situation? Yeah, we can actually FOIL this. Okay. So it's going to be 1 times 1, which is 1, minus the sine of theta plus the sine of theta. Oh, nice. They cancel out, right? Minus sine squared of theta. We're almost there, I promise. All over sine theta cosine theta. And now I have my magical extending paper. Let's see, because I'm going to need some more of it. I am almost there. I have 1 minus the sine squared of theta over sine theta cosine theta, right? Because these two add and subtract to cancel out. Okay, 1 minus the sine of theta is the same as the cosine squared of theta, thanks to my Pythagorean identity. So I have cosine squared of theta over the sine of theta cosine of theta, which when I cancel out one of the cosines, I'm left with the cosine of theta over the sine of theta, which is the same as the cotangent of theta. Voila. Right? So that's one way that we can, or that's a way that we can simplify that. So all that to say that, yes, the secant of theta minus the tangent of theta times the cosecant of theta plus 1 does equal the cotangent of theta. Okay, so I know it's a lot, but it's just basically a game of how well can you simplify? I honestly think that 39 through 43 are the three or the four hardest ones that there are to do. Once you get past that, they actually get a little bit easier again. Oh, good, Sarah. I'm glad to hear it. Yeah, it's a lot of like detail, but it's instead of trying to use the unit circle to figure out what the values are, this is just kind of playing with the functions algebraically to find it. I'm just trying to think if we want to do one more. Which one do we want to do? Let's do 46 because that should be kind of a quick, easy one. Let me see what Sarah says. It's like you're in a submarine decoding the enemy secret battle plan transmissions. Exactly. And you have an amazing flag. You have an amazing flag to help you out, right? Yeah, I think we can do 46 pretty quickly and easily. So some of them aren't as scary as this one. Like 40 took a long time, but 42, when I did 42, not so bad. Just draw a random line here. So they're not all this heavy. It's just, and you sometimes, I might not have even done that in the fastest way. You might have had a faster way to do that. So it's not always, it's kind of, oh, I could do this and then that would work and then this thing. Okay. All right, so let's do 46. Again, it's the same thing. I don't know what the difference is between the two. Verify algebraically. Oh, one says use a table feature, one says use a graphing feature. I'm fine if you use a table or a graphing feature. So I'm not picky if it says table or graphing. You can use either one of those. So 46 is the sine of theta times the cosecant of theta minus sine squared of theta. Okay, and we want that to equal the cosine squared of theta. So again, let's kind of get everything to sine and cosine, especially because we want cosine squared, right? So the sine of theta, leave that alone. The cosecant of theta, right, is equal to 1 over the sine of theta minus the sine squared of theta. Okay, well, the sine of theta times 1 over the sine of theta, those cross each other out, and you're left with 1 minus the sine squared of theta. So then if I look at my Pythagorean identities way back here, right, I know that sine squared plus cosine squared equals 1. So if I subtract sine squared from both sides, 1 minus the sine squared is the cosine squared. So another way of writing this is the cosine squared of theta. So now we proved that they equal each other. Okay? So I know it's a lot of just like detail stuff, but it's really just playing with the equations, trying to come up with a different way of writing the same thing. My tip to you would be two things. One, keep this chart handy when you're doing your work, right? And know that you can rewrite these in different ways. And then my second tip would be, whoa, that's a lot of writing. My second tip would be when I'm simplifying these, I think it's easiest if you put everything in sine and cosine. Because if you get everything to sine and cosine, then you can really start canceling stuff out and figuring out what properties that you can use. Some people, I mean, sometimes you can look at it and you don't have to do that, but for the majority of them, I would put them into sine and cosine and kind of figure it out. Okay. Well, have fun on your submarines battling or decoding secret messages and or doing your math homework. And thank you guys for coming today, and I will see you on Monday.
Bye.
Bye,
See you
guys.
Monday.
Bye, thanks. See you.